Okay, we're now going into areas that were not covered in Math 100. We didn't do Chapter 6, 7, or 8 at all. So these are new areas, but we build on a lot of material that we reviewed in Math 100 and that you've reviewed in Math 105 so far. So we're now going to be dealing with what are called rational expressions. And generally a synonym for rational here is a fraction. So expressions that contain fractions and equations that contain fractions and functions that contain fractions. So these are the topics. We'll be dealing with simplifying rational functions, multiplying and simplifying, dividing and simplifying, and then we're also going to look at a particular term, the vertical asymptote. What these do is when we have a graph, it sort of defines a vertical line that relates to the graph. So we'll be showing you that as we go on. But as we move on, let's take a look now at some of the vocabulary. There are only 4 words, and I believe some of them you know already. So in reviewing these, an expression that consists of a polynomial divided by a non-zero polynomial is called a rational expression. That is, a polynomial divided by a polynomial, and we often give it this qualifier where this denominator cannot equal 0. We'll be doing some of those when we define the domain of the denominator. Remember, we cannot have the denominator as a 0. Those are undefined. And to divide 2 rational expressions multiplied by the reciprocal, so if we have like 1/3 and we multiply that by its reciprocal, which is 3 over 1, remember the definition of a reciprocal is the number you multiply something else by so that the product is 1. And then the graph of many rational functions approach one or more vertical asymptotes. So here would be a parabola, and then this line right down the middle. Actually, it's called the axis of symmetry here, but that would be an asymptote as well. Okay. So what we're looking for now in terms of 5 and 6 is these are rational functions. They're fractions. And we want to find the function value indicated provided a value exists. Now, if any of these values of x here, a 0, a 3, a -1, make our denominator a 0, then the function doesn't exist. So again, a strategy for doing this would be to make a t-chart to help organize your answers and kind of tie it into things we've done in the past. And then these are your values of t over here, -1, a 1, and a 3. Now again, as you put any of these into your system and do your substitution, if they make the denominator a 0, then that is undefined. That value does not exist. So let's do that. So as we look at number 5, and if we take x as a 0, again you need to put it in there very carefully. So 0 squared is 0, minus 0 is 5, and then 4 minus 0, we're left with the fraction 5/4. And that's what we have here. And you do the others in a similar way. And then I thought number 6 was interesting in if we put a 1 where t is, so 1 cubed is 1, minus 5, that would give us a negative 4 in the top. And then 1 squared is 1. This will be 1 minus 2 plus 1. Now notice we have 2 minus 2, which gives us a 0 in the denominator. So if t is 1, no solution or no value exists, because this is undefined. Now, as we look at example 7 and 8, they want us to find the domain. So the strategy is, what would make our denominator a 0? So we just equate our denominator to 0. And here, if x is 0, then our denominator would be a 0. But any other number is good. So I think we did one like this already on a number line. And we said, in real numbers, x cannot be a 0. But every other number is good. So the way to write that in interval notation is from negative infinity up to 0, but not including 0. And then that's in union with, again, starting at 0, but not at 0, but from 0 to positive infinity. Or simply, x cannot be 0. It's a real number, but x cannot be 0. And here, if you realize this is going to factor into its conjugates, so this is p plus 5, p minus 5. So here, x is a real number, but I guess it's the letter p, but p cannot be negative 5 or a positive 5. And then in interval notation, it will look like this on a number line. Here goes up to 5, but negative 5 is not included. And then in interval notation, that's the graph, it looks like this. Okay, let's go on. Now our strategy for number 9 is we want to remove factors equal to 1 as we simplify. So I look at 48 and I realize that is 3 times 16. And I look at 32 and that is 2 times 16. So 16 divided by 16 is a 1. And then I modified my a to the third to make it a to the second times a. I left that out. And my bottom, I now have a to the second. And then I look at my b, I put b, and b to the fifth I changed from b to b times b to the fourth. I can put little dots there, but whatever helps to clarify. Now, I have factored out here an a to the second. So this is going to be a 1. And I'm factoring out this b. That's going to be a 1. So what am I left with? Well, on the top, I'm left with a 3a. And on the bottom, I'm left with a 2b to the fourth. Now notice there are no more common factors that I can cancel out. Now you might have started here with a 2, and got a 24, and this would have been a 16, and then taken a whatever out of there to keep going down. But the process that you want to eventually get to is you're taking out common factors that when you divide it by itself give you a 1. Now here I probably would have used the technique of subtracting a 2 from there to get a 1, and bringing this down and ending up with a 4. But I wanted to show you the technique of removing factors equal to 1. Now as we look at number 10, first of all, you can never just do this, because you're only allowed to cancel out common factors. But here I see I can take a 6 out of there. And when I take a 6 out of the top, I get an x plus 5. Now I can take a 6 out of the bottom, and I get an x minus 2. Now what are common factors? Well, the 6's are. So my final answer is x plus 5 over x minus 2. Now remember, you cannot cancel the x's here, because these are not factors now. Here they're factors. These are terms. You can't cancel out common terms. So that's a no-no. Okay, now as we go on to number 11, they want us to do something similar. Well, we're going to factor out a 2 here and get x minus 4. And we're going to factor out an x here and get x minus 4. So now we see the factor containing the variable is the common factor. So we cancel this out, and our answer becomes 2 over x. And here's where your factoring skills come in. These are the difference of perfect squares, which will factor into their conjugates. This is a perfect square trinomial, which will factor into x plus 6, the quantity squared, but I'm going to write it out this way so I can cancel out my common factors, and there is your answer. Now here I saw that my 3p was positive. So if up on the top here, and we had practice in Math 100 on this, that if we take out a negative 4 out of this, then this would be a negative 4 goes into there, and this would be a positive 3p. And if I use the commutative principle to switch these two around, I end up with this, which is now exactly the same as my denominator. So I can cancel these out, and I'm left with a negative 4 over 1 that I just write negative 4. Now they also asked which values would make our denominator a 0. So I equal the denominator to 0, and I say that p is all real numbers, but p cannot be 4/3. Now for this one, again, we're looking to factor it and factor the bottom. Now I could just factor this, TT 5, 2, and I FOIL that, and that checks out. And this one is TT, and this is a 5 and a 4, and our middle term needs to be negative. So these will now cancel out, and that is our answer. Now notice when we do our answers, we have to use our original one, equal it to 0. So here x cannot be a -4, or t, and t cannot be a 5. So these are values that t cannot be equal to, but otherwise all real numbers. This is to, and we're not going to do this a lot, but every once in a while they'll ask us to remember that there are certain values of the variable that are in the denominator that if they are a certain value cannot be an expression because it makes the example undefined. Okay, as we go on to simplify, again, they're not asking us to find out what would make the denominator as 0 here, but those qualifiers would be in status, so to speak. Here, this can't be simplified anymore. I got to put the t there. But here I could take a 3 out of there and get this. Here I can take a 4 out of there and get that. And I have to do a little more modification of the answer there. So this now will cancel with that. And I'm left with 16 over 3, but I can take out one of these. So this will give me here a 2. So my final answer is 16 over 3t squared. Otherwise, you could pick up a bonus point there, or a pen, or something. Okay, let's look at number 16. This gets a little bit tedious here. Sort of like 4 of our problems in chapter 5. And this is just one example. But here we can take out an x. Here this factors nicely into this. This is a perfect square trinomial that will factor into that. Here I can take out an x squared, but then I'm left with the difference of perfect squares that will factor into its conjugates. So I'm going to take the eraser and get rid of this through the magic of our technology here. Now what happens? Well, let's see. I can factor out this with one of those. So I'm just left with an x there. My x squared, well, x minus 2. X minus 2 will cancel out. X plus 3 with x plus 3 will cancel out there. And then anything else? No. So in my numerator here, I'm going to have x plus 3. And my denominator, I'm going to have an x. And then one of these, or actually 2 of them. And you could write that this way. Look at this. I noticed again these seem to be in the wrong order and the signs are not correct or the way I'd like to have them. So I'm going to factor out a -1 out of this. That just reverses these signs. And then out of here I'm going to factor out a 10, and let me put that 3 in there. There you go. Okay. And I saw another little error. It never hurts to check your work. Okay, so when I distribute this, I get that. So this is good now. Now up here, again, the y, I like to see a positive y. So I'm going to factor out of this a -5. And then I'm going to reverse these, as I showed you in an earlier lesson, that this then becomes 9y squared minus 1 when these are switched around. So let's look at this. Now this is the difference of perfect squares, which will factor into this. So I'm going to get rid of this one here now, so as not to confuse that too much. Okay, so I factored that into its conjugates, and this is what we had, and I factored the bottom here. So what do we have? Well, this will cancel with this. This will cancel with this. Now here I have a negative times a negative, which will make that positive. That's good. Now I have a 5 here that will go once into the 10, which will go twice. So what am I left with? This, which is 3y plus 1. I need my 2 and my y minus 1. And you could leave it in this factored form. That's how MATLAB will use it. Showing lots of items that we've done previously, but all combined into one problem. Notice when we could factor out a common a here, we get this. Now here, this is the difference of perfect cubes, which will factor into parentheses with 2 terms and one with 3 terms. And that was a technique we had in chapter 5. And then here, if we factor out a 4, we get this. And here, if we factor out a 4, we get a squared minus 4, which is the difference of perfect squares, which will factor into its conjugates. And then here, if we take out a 2a from each term, 2a squared, then we're going to get this. All right. Now we go to factor, or cancel out. So, again, doing it on live camera is not always the best way, but hopefully we work it out okay. So our 4 will cancel with the 4. We're going to take out one of our a's with one of our a's here. So this leaves me with a 2a. All of this cancels with this. Alright, so we're left with this times this in our numerator over this in our denominator. And even though it looks pretty complicated, again, it just takes time, and check your work. Okay, going on to number 19, and these next few, we're going to be dividing. So the key is change from division to multiplication by taking the reciprocal of the second term. And here I've kind of factored it a little bit. So what will happen? Well, here this 7 will cancel with this 7. This 9 with this 9. Then we have a, what's left? Let's do some d's here. This d to the first will cancel. This will become d to the 7th. This c to the 5th will cancel, and this will become c to the 2nd. So our numerator then will be 4 times 5 is 20. 3 times 7 is 21. This will be d to the 7th, c to the 2nd. Now, the tape is running a little long. Again, the only major technique in these previous examples is to change them from division to multiplication by taking the reciprocal of the second term and then canceling out. So we had done plenty of those. so you know the technique. Here it's to determine the vertical asymptote of the graph of each function. We factor it, and these cancel out here. And to find the vertical asymptote, we take what is in the denominator, equal it to 0, and we find that x is 3. That is your vertical asymptote. Now, some of the instructors may not include this in the class, but this is some pretty higher level math here. And then here, when we factor it, and we've done similar things, we end up with the variables canceling out. So when we have that, there is no vertical asymptote. Okay, winds this up.